In 1945, humans split the atom and accidentally made you radioactive. Before July 16, 1945, there was no isotope cesium-137. It didn't exist. Not in soil, not in oceans, not in rocks, nowhere on Earth, or even in the solar system. 5:29 a.m. First ever nuclear bomb detonation, and it's everywhere. Right now, as you watch this video, there is nuclear fallout sitting in your bones. We accidentally created a universal, made after 1945 sticker and put it on the entire planet. So, if we can leave a timestamp like this, maybe the universe has been recording the date on everything since the very beginning, and we just need to learn how to read it. For most of human history, we had no idea how old anything was. People knew some things were older than others. A fossil clearly looked older than a fresh bone, a mountain older than the city built next to it. But how much older?
In 1600s, an archbishop named James Ussher read the Bible extremely carefully, cross-referenced ancient Egyptian and Hebrew chronologies, did the math, and concluded the Earth was created on October 23rd, 4004 BC.
Which is specific and wrong. 16th, 17th century, it was considered serious scholarship. Basically, the best answer anyone had.
But then geologists started looking at rock layers called strata and realized, wait, these layers took really long time to form, like way longer than 6,000 years. But even then, they could only say old or very old. They had no actual numbers.
The problem seemed basically unsolved, until physicists handed geologists the most precise clock in the universe. Let me show you something. This mineral here is called charoite. It is pretty, but slightly radioactive. If you hold a Geiger counter next to it, you will get something, let's see. It went up to 0.87 microsieverts per hour. That's the unit for radiation dose. Like many minerals, it contains traces of radioactive elements. This here contains a small trace of thorium, genuinely measurably radioactive. With higher numbers of radiation, the counter is making that famous noise, a clicking sound. This one is programmed not to react to levels below 0.6, because below that, we're talking about completely normal background radiation, the kind that's everywhere.
Right now, sitting in this room, I'm getting around 0.05 to 0.3 microsieverts per hour, same as you are wherever you're watching this. A long-haul flight gives you about 3 microsieverts per hour, because at altitude, there is less atmosphere shielding you from cosmic rays. A chest X-ray is around 100 microsieverts total, but during X-ray, you're exposed to radiation for a very short period of time, which is also important in terms of harm.
So back to our mineral. At the 0.87 mark, we heard the clicking of the counter. That clicking is the decay, atoms breaking down in real time on my table. Thing is, they do it at perfectly fixed, unchangeable rate. Always the same, no matter what. Heat them up, cool them down, crush them, dissolve them, launch them into space, same rate. The decay of a radioactive isotope is one of the most stable constants in all of physics. Nothing changes it. And that means it's a clock.
Say you start with 1,000 atoms of radioactive element, and you know its half-life is 1,000 years, meaning every 1,000 years, exactly half the remaining atoms decay. Find a sample with 500 atoms left, 1,000 years have passed. 250 atoms, 2,000 years. 125, 3,000, and so on. The atoms are counting time for you, perfectly, without ever stopping.
This is called radiometric dating. And it's not one method, it's like a collection of clocks. For thousands of years, for millions, or for billions. The only thing you need to know is where the clock started. And nature, it turns out, is pretty good at telling us that too. Carbon-14 is the famous one. Probably you've heard of it. So let's understand how it works.
Up in the atmosphere, cosmic rays, basically high-energy particles flying in from space, smash into nitrogen atoms and convert some of them into a radioactive form of carbon called carbon-14.
Eventually, it gets absorbed by CO2. Plants breathe in CO2, animals eat plants, and boom, everything alive has a steady amount of carbon-14 in it all the time. While you're alive, the C14 level in your body stays constant because you keep eating and breathing. But the moment you die, it starts decaying. No new C14 coming in, and the existing stuff just slowly breaks down. Carbon-14 has a half-life of 5,730 years. So 5,730 years after something dies, half its C14 is gone. Another 5,730 years, half of what is left, gone. So you take a piece of ancient wood, measure how much C14 it contains, compare it to what it should have had when it was alive, and you get an age.
This is how we learned the age of Egyptian mummies, how we confirmed the age of Ötzi the Iceman, a frozen 5,300-year-old man found in the Alps, or dated the Dead Sea Scrolls, a collection of over 900 ancient manuscripts, including the oldest known copies of Hebrew Bible texts.
Good, or I would say perfect, but up to about 50,000 years. And that is nothing in geological time. Because, for example, dinosaurs died out 66 million years ago. So for that, we need to find different clocks. Bananas. I'm serious. Every banana you've ever eaten contained a naturally radioactive isotope called potassium-40. Don't freak out, bananas are harmless. The amount of potassium-40 is tiny in them, but it's a fact that we've been eating radioactive material, which, by the way, is one of our best time tools.
Potassium-40 decays into argon-40, hence the name potassium-argon dating. Half-life 1.25 billion years. When a volcano erupts and lava cools into rock, any argon gas that was in there escapes. The clock resets to zero. From that point, new argon starts accumulating from the decaying potassium trapped in the rock. Measure the ratio of potassium to argon, get the date the rock solidified. Simple.
This technique, and its more precise cousin, argon-argon dating, is how we date ancient hominid fossils. Not the bone itself, bone is too porous, so gases leak, but the volcanic rock layers directly above and below where the fossil was found. Sandwich the fossil between two dated layers, and you've got yourself an answer.
This is exactly how we know Lucy, the famous Australopithecus fossil, found in Ethiopia, is about 3.2 million years old. Scientists used argon-argon dating on volcanic ash layers just above and below where she was buried.
Then comes the heavy artillery of radioactive dating methods. Uranium-lead dating. Uranium-238 decays into lead-206, half-life 4.47 billion years. Scientists use it on tiny crystals called zircons, like those here. They're basically microscopic time capsules. When a zircon crystal forms, it locks in uranium, but it rejects lead. So any lead you find in a zircon later is purely from uranium decay. Zero contamination from the outside. It's a sealed system.
The oldest zircons ever found are from Jack Hills, Australia. They're 4.4 billion years old. Ancient, but still younger than Earth itself, because the early planet was too hot and chaotic for rock to survive. And the age of the Earth itself, 4.54 billion years, comes from uranium-lead dating of meteorites that formed at the same time as the solar system, just floating in space, untouched for billions of years until we found them.
So essentially, we found our planet's birthday by measuring rocks that fell from the sky. But let's go back to the nuclear weapons for a moment, because the newsfeed is not nuclear enough.
So when nuclear bombs are detonated in the atmosphere, they massively spike the amount of C14. Between 1951 and 1963, the peak years of above-ground nuclear testing, the concentration of C14 in the atmosphere nearly doubled compared to natural levels. Every living thing on Earth absorbed that spike. Every plant, every animal, every human who was alive during or born after those years carries it in their tissues. Scientists call this the bomb pulse.
In 1963, the Partial Nuclear Test Ban Treaty stopped most above-ground tests, so C14 levels started falling as the extra carbon got absorbed into oceans and soil, tracing a very specific measurable curve ever since. If you take a sample of organic material and measure its C14 level, and it matches a point on a bomb pulse curve, you can often pin down the date of its creation to within 2 or 3 years. Sometimes even less. This has been used to date wine vintages, forensic investigations to determine when a person died, or even their birth year from tissue samples.
Scientists used it to determine the age of bowhead whales from amino acids in their eye tissue. Turns out some of them are over 200 years old. There's a bowhead whale alive today that was born before Napoleon was defeated at Waterloo in 1815.
And the crazy part, the same method has been used to catch art forgers.
The Peggy Guggenheim Collection, Venice, one of the most famous private art collections in the world. Somewhere in their storage for over 40 years sat a painting, a cubist work, believed to be part of Fernand Léger's celebrated series, painted between 1913 and 1914.
The painting was worth a fortune. There was just one problem.
In the 1970s, a leading Léger scholar and art historian, Douglas Cooper, looked at it and said, "I don't think this is real."
Nobody could prove he was right. Nobody could prove he was wrong. Art historians argued for decades. The painting never went on display. It just sat there in storage, an unsolved question with a price tag attached, for 40 years. And then, as always, physics came to the rescue.
Scientists from the Institute for Nuclear Physics in Florence asked for a sample. Not a big one, a tiny fragment from a folded, unpainted edge of the canvas.
They measured its radiocarbon content, plotted it against the bomb pulse curve, and got an answer. The canvas was made in 1959. On the other hand, Fernand Léger died in 1955. That's it. 40 years of debate, settled by a piece of canvas smaller than your thumbnail and the radioactive fingerprint of Cold War nuclear tests. Turns out, you can fool art historians for 4 decades, but you cannot fool the bomb pulse. So we can date things thousands of years back with C14, millions of years back with potassium argon, billions of years back with uranium lead. But what's the limit?
Scientists have dated individual stardust grains found inside meteorites. Grains that formed in dying stars before our solar system even existed. These are called presolar grains, and they were found in the Murchison meteorite, which fell in Australia in 1969. The oldest of these grains are 7 billion years old, so they are older than Earth and our Sun. They just floated through space for billions of years, got swept up into a meteorite, fell to Earth, and we found them.
7 billion year old stardust in a meteorite, and you can find it in a museum, in several museums actually. Radioactivity isn't the only clock we have.
Tree rings going back 12,000 years built by overlapping patterns from living trees and ancient timber.
Quartz crystals that absorb background radiation from the soil and store it. Heat them in a lab, they release it as light. The brighter the flash, the longer they've been sitting there. That's how we date pottery, not from how it looks, but from the light it holds inside.
And of course, Antarctic ice. Scientists drill out cylinders going back over 1 million years with tiny bubbles of ancient air trapped inside. They crack them open and they read the weather from before humans existed.
The universe has been leaving timestamps on everything, in every material, in every possible way, since the very beginning. We just had to be curious enough to learn to read it. Thank you for your time. See you in the next video.